Hi, I am a tutor in Uplatz. Today we are going to discuss about FPGA design part 23, design and implementation of digital signal processing systems and introduction. What is the signal processing implementation options and design issues? General purpose microprocessors, GPP, multimedia enhanced and native signal processing, programmable digital signal process, PDSP, multimedia signal processing MSP, application specific integrated circuit ASIC, Re-configurable signal process. Issues in DSP architecture and projects provide students with a global view of embedded microarchitecture implementation, options and design methodologies for multimedia signal processing, the interaction between the algorithm formulation and the underlying architecture that implements the algorithm will be focused. Formulate algorithm that matches the architecture, design novel architecture to match algorithm. Issues to be treated in projects, signal processing, computing algorithms, native signal processing, multimedia extension, algorithm representation, programmable DSP, algorithm transformation, and folding, very long instruction word, VLAW architecture, Re-configurable Computing and FPGA, systolic array and design methodologies, mapping algorithms to array structures, signal processing, mathematics, cortex, distributed means, scope of design, application, video, audio, communication. What is signal? A signal is a measurement of the physical quantity of a certain medium. Examples of signals, spatial patterns, written documents, pictures, videos, gestures, facial expression, audio patterns, voice, speech, music, change patterns of other physical quantities, temperature, EMB, etc. Signal contains information. Medium and modality. Medium, physical materials that carry the signal, paper, visual patterns, handwriting, etc. Air, sound, pressure, music, voice, various video displays, CRT, LCD, modality, different modes of signals over the same or different media. Examples, voice, facial expressions, and gestures. What is signal processing? Way to manipulate signal. It's in its original medium or an abstract representation. Signal can be abstracted as a function of time or spatial coordinates. Types of processing, transformation, filtering, distribution, recognition and classification, coding, compression, synthesis and reproduction, recording, archiving, analyzing, modeling. Signal processing application, communication, modulation, demodulation, modem, channel estimation, equalization, channel coding, source coding, compression, imaging, digital cameras, scanner, STTV, DVD, audio, 3D sound, surround sound, speech coding, recognition, synthesis, translation, virtual reality animation, control, hardware, drive, motor, robotic and intelligence systems. Digital signal processing. Signals generated via physical phenomena are marked in that their amplitude are defined over a range of real complex numbers. The domains are continuous in time and space. Processing analog signal requires dedicated special hardware. Digital signal processing concerns processing signals using digital computers. A continuous time, space, time signal must be sampled to yield countable samples. The real complex value samples must be quantized to fit into internal wavelength. Signal processing system. A2D DDA signal processing. The task of digital signal processing DSP is to process sample signals from analog to digital, A2D analog to digital converter and provide its output to the DDA digital analog converter to be transferred back to physical signals. Implementation of digital DSP system platforms, native signal processing with general purpose GP processor, GPP, multimedia extension, MMX instructions, programmable digital signal process, PDSP, media processor, application specific integrated circuit ASICs, Re-configurable Computing with field programmable data arrays, FPGA requirements, real-time processing must be done before a specific pre-specified deadlines, streamlined numerical data, sequential processing, fast automatic processing, high throughput, fast data input output, fast manipulation of data. Now, how fast is enough for this? It depends. Real-time requirements, data capture speed must match sampling rate, otherwise data will be lost. Example, in verbal conversation, delay of response cannot be exceed 50 milliseconds end-to-end. Processing must be done by a specific deadline, a constraint on throughput, different throughput rates for processing different signals. Throughput was proportional to sampling rate, CD means 44.1 kilohertz, speech 8 to 22 kilohertz. Video depends on the frame rate, frame size, etc. Range from 100 second hundreds of kilohertz to megahertz. Early signal processors implemented with either mainframe computer or special purpose computers, batch processing rather than real-time streamed data processing. Algebraic processing speed is the main concern. Key approach: faster algorithms. Faster algorithms reduce the number of arithmetic operations, reduce the number of bits to represent each data. Most important example: fast Fourier transform. Computing Fourier transform, discrete Fourier transform, x of k is equal to sigma n is equal to 0 to n minus 1 of x of n into exponential minus 2 pi n k by n. X of n is equal to 1 by n. Sigma k is equal to 0 to n minus 1 of x of k into exponential of 2 power 2 pi n k by capital N. To compute the n frequencies x of k and k greater than or equal to 0 less than or equal to n square complex multiplications. Fast Fourier transform reduce the computation to order of n log n to base 2 complex multiplications, make it practical to process large amount of digital data. Many computations can be speed up using FFT down of modern digital signal processing. Evolution of microprocessor. Microprocessor implemented a central processing unit or single chip. Performance improved from 1 megaflop 1993 to 1 gigaflop or above. Word length, number of bits for register, database, address space, etc. increases from 4 bits to 64 bits today. Clock frequency increases from 100 kilohertz to 1 gigahertz. Number of transistors increases from 1K to 15 million. Power consumption increases much slower with the use of low power supply. Voltage 5 volt drops to 1.5 volt. Native signal processing, general purpose, use GPP to perform signal processing tasks with no additional hardware. Example: soft modem, soft DVD player, soft impact player. Reduce hardware cost, may not be feasible for extreme throughput tasks. It is interfering with other tasks because GPP is tied up with NSP tasks. MMX multimedia extension instructions, special instructions for accessing multiple data may share the same data path with other instructions, or work on special hardware modules, make use subword parallelism to improve numerical calculation speed, implement DSP specific arithmetic operations, example saturation arithmetic operations. As ASIC, the application specific ICs, custom or semi-custom ICs, chipsets developed for specific functions suitable for high volume, low cost production, example, MPEG codec, 3D graphic chip, etc. ASIC becomes popular due to availability of IC foundry services. Fabless design houses turn innovative design into profitable chipsets using CAD tools. Design automation is a key enabling technology to facilitate fast design cycle and short time to market design. Programmable digital signal processor, PDSPs. Microprocessor designed for signal processing applications, special hardware support, multiply, accumulate, MAC ops, saturation and panic ops, zero overhead loop ops, dedicated data IO ports, complex address calculation and memory access, real-time clock and other embedded processing and support. PDSP were developed to fill a market segment between GPP and ASIC. GPP flexible, slow, ASIC fast but inflexible. As VLSI technology improves, the role of PDSP change over time, cost, design, sales, maintenance, upgrade. performance. Multimedia Signal Process Specialized PDSP is designed for multiple applications, which is multi-processing systems with a GPP4 plus multiple function modules. PLI W like instructions to promote instruction level parallelism, dedicated IO and memory management units, main application video signal processing, impact, SR324, SR263, etc. This 3D sound graphic engine for 3D rendering. Re-configurable computing using FPGA. FPGA field programmable gate array is a derivative of PLD, programmable logic devices. They are hardware configurable to behave differently for different configurations, slower than ASIC but faster than PDSP. Once configured, it behaves like an ASIC module. Users of FPGA rapid prototyping run fractional ASIC speed without fabrication delay. Hardware accelerator using the same order to realize different function modules as a hardware. Low quantity system deployment. Characteristics and impact of VLSI. The term VLSI but large scale integration is coined in 1970. Usage of VLSI microprocessor, general purpose programmable DSP, embedded microcontroller, application specific IC field programmable gate array, impacts design methodology, performance, power. Characteristics: high density, reduced feature size, 0.5 micrometer to 0.16 micrometer. Percentage of wire routing area increases. Low power, high speed, decreased operating voltage, 1.8 volt on board. Increased clock frequency by 500 MHz 1 GHz. High complexity, increased transistor count, 10 million transistors higher. Shortened time to market. Today, 6 to 12 months. Design issues: given a DSP application, which implementation option should be chosen for a particular implementation option? How to achieve optimal design? Optimal in terms of what criteria? Software design, NSP, MX, PDSP, MSP algorithm are implemented as programmed. Other often still requiring programming assembly level manually. Hardware design, ASIC, FPGA algorithms are directly implemented in hardware modules. Sample and word code design, system level software hardware code design, system level design methodology. Design process model. Design is the process that links algorithm to implementation. Algorithm operation dependency between operation determines a partial ordering of execution can be specified as a dependence graph. Implementation assignment. Each operation can be realized with one or more instruction software or one or more functions modules. Hardware scheduling depends. Hence, relations and resource constraints lead to a schedule. A design example: consider the algorithm y is equal to sigma k is equal to 1 to a k. Okay. Program y is equal to 0 or k is equal to 1 to n 2. Y of k is equal to y of k minus 1 plus a of k star x of k. N y is equal to y n1. Operation, multiplication, addition. Dependency: y of k depends on y of k minus 1. Dependence graph: y0 with a1 x1 multiplied and added to y0. a2 x2 multiplied to y2. A and xn multiplied and added to yn minus 1 to get yn. Software implementation: match each star operation to multiplication instruction, match each plus operation to add instruction, allocate memory space for AK, XK, and YK. Schedule the operation by sequentially execute. Y1 is A1 into X1, Y2 is Y1 into A2 plus X2, etc. Note that each instruction is still to be printed in hardware. Hardware implementation: map each star operation to multiplier and plus operation to order. Interconnect them according to the dependence graph. Eventually, an implementation is realized with the hardware. However, by using the same hardware to realize different operations at different time, scheduling, we have a software program. Bottom line: hardware software design. There is a continuation between hardware and software implementation, and design must explore both simultaneously to achieve best performance cost trade-off. The designer has two approaches: matching hardware to algorithm. Hardware architecture must be matched the characteristic of algorithm. ASIC architecture is designed to implement specific algorithm and hence can achieve superior performance. To formulate algorithm to match hardware, algorithm must be formulated so that they can best exploit the potential of architecture. Example, GPP, PDSP architecture. One must formulate the algorithm properly to achieve the best performance to minimize the number of operations. Algorithm reformulation, matching algorithm to architectural features similar to optimizing assembly code, exploiting equivalence between different operations. Reformulation methods equivalent of ordering of execution A plus B plus C is equal to A plus B plus C. Equivalent operation with a particular representation. A star 2 is the same as the left shift or a by one bit in binary representation. Algorithmic level different filter structures depending implementing the same specification. Algorithm reformulation to exploiting parallelism, regular iterative algorithms and loop reformulation, well studied in parallel compiler technology, signal flow data flow representation suitable for specification of pipeline parallelism. Mapping algorithms to architecture, scheduling and assignment problem, sources, hardware modules, and time class, demands operations algorithms and throughput, constraint optimization problem, minimize resources, objective function to meet demands constraints. For regular iterative algorithm and regular process, algebraic mapping. Mapping algorithms to architecture, irregular multiprocessor architecture, linear programming, heuristic methods, algorithms reformulation or recursions, instruction level problem, MMX instruction programming related to optimizing compilation. Arithmetic, Cardic, compute elemental function, distributed arithmetic, ROM-based implementation, redundant representation, eliminate carry propagation, reduce number system. Low power design is important in DSP. DSP level low power design, logic level low power design, low power design, algorithmic level low power design. What is an LFSR and MISR circuit? LFSR and MISR, linear feedback shift register and multiple input signature register circuits are two types of specifically connected series of flip-flops with some form of XNOR feedback. They are used in many applications for generation or detection of pseudo random sequences. LFSR block diagram, it consists of 4 flip-flops with clock and input, and with a adder in between for each one of the output and the final output. By changing the feedback path to tap, only a certain flip-flops maximum, then sequence can be produced. Maximum is equal to 4. Polynomial 1 is equal to x cube plus x power 4. Maximum length 2 power n minus 1 is equal to 4 minus 1 is 16 minus 1 is equal to 15. Problem with this type of LFSR. Setup time feedback for D1 has to go through n XR before arriving. N logic delays slows down circuit performance may need to run at speed. Solution is to have many input XR feeding D1 input on logic level. State 00 is illegal. When FF power up, they must be initialized with valid data. Solution is to use XNOR instead, still produce PRBS, but all zeros is a valid state. Maximal length sequence, output sequence 1000, 1001, 100, 1010, 101, 1111, 0001. The stage is not S14 is shown in figure, S15 is equal to S0, S16 is equal to S1. MISR block diagram, generic MISR block diagram is shown in figure. Multiple inputs 4 bit wide, D1, D2, D3, D4. LFSR MISR built self-test of logic devices, cyclic encoding, decoding, cyclic redundancy check, pseudo random generator, pseudo random binary sequence generators, spread spectrum, CDMA applications. Built-in self-test devices can be self-tested at speed by incorporating LFSR MISR circuits into the design. Testing can occur when the device is operating or while in an idle mode. An LFSR generates a pseudo random test pattern. A small LFSR with the appropriate feedback can generate a long sequence of apparently random data. Built-in self-test continue. The pseudo random pattern that is generated by the LFSR is fed through the logic under test then into the MISR. MISR would essentially compare the result with the known good signature. If the result is the same, then there were no errors in the logic. Refer to Dr. Perkovsky's built-in self-test presentation test. Spectrum PRBS, because PN signals have good autocorrelation, they are used in code division multiplex access spectrum communication systems. For random noise generation sequence are used to effectively spread the overall bandwidth of CDMA signal for every data bit that is to be transmitted. A PRNS is substituted. The information rate remains the same, but the new bit rate is dramatically increased. One is set to that value pattern, 0 is set to different bit pattern. Below is a diagram showing an efficient arbitrary PRBS generator. By modifying the tab config 0 is to 3 and selecting the proper output, the circuit can generate many different random binary sequences. Practical LFSR and MISR circuits are used in many applications. As technology continues to advance, more and more devices will be developed that will utilize the unique properties of this powerful circuit. Built-in self-test program CDMA applications are but a few many places where LFSR and MISR circuits are used. Practical combinational multipliers. What is a combinational multiplier? A combinational multiplier circuit is comprised of multiple shift registers, adders, and some control logic. Yes, multiplier is performed by addition and shifting. Typical generic multipliers are slow, often taking multiple clock cycles to a computer product. Computers without dedicated multipliers must perform a multiply using this method. Example of a 4-bit multiplication is shown here. So you require so many operators and adders and going to get the product term. The generic serial multiplier block diagram is shown here. 8-bit parallel adder and so many flip-flops and circuit. So what is wrong with this table multiplier? For an n by n generic multiplier, it takes n clock cycles to get a product. There is too slow, inefficient use of hardware. Types of multipliers: standard binary multiplier, one's complement, two's complement, universal, etc. Recoded multipliers, canonical signed digit, both, etc. Serial parallel multiplier, as iterative cellular array multipliers, Wallace, Pesaris, Bowagis, ROM-based multiplication, constant coefficient multipliers, logarithms, etc. Multiplier application, general purpose computing, this is another finite impulse response filters, convolution. ROM-based constant coefficient multiplier with some DSP applications such as FPGA generation and convolution, where the coefficient remains unchanged and high speed is a requirement. Use a lookup table approach to multiplication is quite common. Using the known coefficients, every possible product is calculated and programmed into a lookup table or RAM. The unknown multiplicand input data is used as an address to the lookup product. This method results in a very high speed multiplies. However, it requires large amount of storage space. ROM-based use ROM to generate partial products. Some all the partial product ROM outputs. So here 2 8-bit ROM lookup table is given, and then it is added to get the 15-bit, 16-bit output. Practical combinatorial multiplier, general shift and type of multipliers are slow. People will always be searching for methods of performing fast multipliers. Multipliers are used in many areas. General purpose math for PCs and DSPs, FPGA filters, convolution, etc. Applications are just a few of the places where multipliers are utilized. References are given here. The source is taken from this. Thank you.